Welcome to demo video 3 on deep learning in this course B10 Python for AI. We're going to talk about now is a very brief introduction to deep learning, which you mentioned already in the intro videos. So deep learning can often use pre-trained models built using related data to apply more complex models. That's how we use it more in practice. So deep learning is very effective for very, very complex models where we have many, many layers across here, where we are able to implement feature extraction classification over a series of steps, unlike machine learning approaches, which have far fewer layers present and involve manual creation at the start to identify what's most of interest. We also have things like activation functions, which allow the data and the features associated with that data to be transformed into nonlinear spaces as well. So the deep learning models can be very, very effective, but require GPU compute to work effectively. So these activation functions that allow nonlinear transformations include ReLU, sigmoid, and softmax. When we're iterating through our stages, we have loss functions to compute things like the mean squared error for regressions or the cross entropy for classification. Either way, we want to minimize the losses during this optimization process. We also have population, where the algorithm is computing how each weight contributed to the error, and then it adjusts the weights to try to reduce this. And this can be implemented in the Python libraries PyTorch and TensorFlow. We also have optimizers, which control how much and which direction the weights are adjusted at each step. We have dropout and regularization. Dropout randomly switches off neurons during training, preventing the network from memorizing training data and overfitting. In Collab, we can apply GPUs by changing the runtime type to, for example, T4 GPU. We don't need it in our example here. It's not necessary. But if we're doing something more complex, that would be an option. But we may need to go to a higher tier for Collab to do that effectively on large data. So for our purposes in this demo article, we're just using the CPU version. So what we can think about is then what is a neural network? So basically with three features as input, our colony size, zone of inhibition, and growth rate. We have 64 and 32 neurons, and then we got our output as a classification as resistant or sensitive. E-connections of weight is adjusted by backpropagation to reduce the prediction errors. So there's feedback between the different layers that are present here. And what we're trying to do is our network here is actually relatively small to allow it to train very quickly on a CPU. We'll also find that if we had fewer batches present, it wouldn't really make a difference. So our setup is that we're using TensorFlow, and we're going to use a standard feed to make it reproducible. And then we're going to use this to apply these models to our same data set we had before. And what we're doing is we're using a ReLU activation function, a certain dropout score, and we're also going to try the sigmoid activation function and the atom optimizer mentioned before as well. So this is setting up our model to create the model summary. So this is our model summary. We have the layer type, the output shape, and the number of parameters associated with it labeled there. So what we're going to do now is go to Google Colab, where we can see that more effectively. What we can see is that we've installed TensorFlow. We can run our models there and get this output table denoting that information. And then what we can do is use the model.fit function to train our model. And we're determining the batch size there, the number of epochs, and the validation split there. So we've got 20% for testing and 80% for training. And after that, what we're going to do down here is visualize that. So what we're doing is we're basically plotting that to see how effective it is across the whole series here. So what we see is that the validation loss function hit a plateau quite quickly in terms of the number of epochs. And we can see that on the right-hand side as well, is that there's a little variation at the start, which is normal. And then after that, the accuracy doesn't really improve too much for the validation data set. So if we ran that for longer, it wouldn't really make any difference at all. So we can turn this down to, say, 30 and plot that again, and wouldn't really make any difference to what we see here at the end. So that's taking a little while to complete. What we can do, there we go, that's complete now. So what we can see is that I didn't reset it. So we'd have to reset it here to create a new model. So let's come back to that in a moment. And what we can do then is create a confusion matrix based on the output here. Um, so we're looking at the neural network results using the confusion matrix display function that we had before. What we see is that the recall and F1 scores and precision are all very similar to what we had before. And the confusion matrix kind of indicates is that we misclassified 97 samples, so arguably it's a tiny bit better than the previous two models, but it's largely the same. So you can see here how we can apply deep learning to this data set and create similar metrics to what we had there at the start. What we can move on to next is then comparing all three models. So here what we're going to use is ROC curves. So we're going to look at the area under the curve to see how good they are. So we know that area under the curve, a value of 1 is a perfect classifier, and a value of 0.5 is no better than random chance. And what we would expect there is that we know our AUC won't be too high here in this particular instance. So what we're doing is looking at the three different models here with different colors. We're trying to plot their predictions using the ROC curve function and computing the AUC score to look at how good they are. So effectively plotting 1 minus specificity versus the sensitivity. And we see that down here, the dotted line is random chance. What we can see is that there's no substantial differences between the model. Arguably, the neural network model works the best, and the XGBoost option, gradient boosting, the worst, but it depends on exactly which false positive rate is acceptable to you. If we're working over here, our value around 0.1, you can see there's very little difference between them. If we go lower, maybe near 0.05, you can kind of see that the neural network and XGBoost tend to do better than the SVM, although in reality, we'd probably want a larger data set to test that more definitively. We can then also create a summary table containing the F1 stats, the accuracy, and the errors for each of these models to get that as a table so we can compare each of them. And what we see is that the accuracies, the neural network is slightly better. Again, for the F1, for the R group, we see for S group, it's a bit lower, but that's just the random variation we see. The AUC is consequently higher, and the number of errors is slightly lower. So overall, what we can see is that the neural network is very, very marginally better than the other option. So that concludes this part on deep learning and our engagement of applying different AI models and comparing the outputs.